My name is Haruna. I'll be taking you BCH211 General Biochemistry. For this time around, we are going to be looking at dissociation of water. Water undergoes self-ionization in a forward and backward reaction to give you hydrogen, to produce hydrogen ions and hydroxy ions, which are the products of such ionizations. And in such ionizations, again, the equilibrium constant of water is given as the concentration of hydrogen ions multiplied by the concentration of hydroxy ions divided by the concentration or the amount of water. In the above expressions that I just mentioned, the value of water may be taken as having a constant value because the degree of ionization is so small. What that means is that these hydrogen ions and hydroxy ions that are produced during the ionization of water are very small. They are very small, such that it is in taking the ionization constant that one will be able to effectively determine the presence of such ions. So, like I said earlier, the equilibrium constant, which is given as the concentration of hydrogen ions multiplied by the concentration of hydroxy ions divided by the concentration of water, is changed to the equilibrium constant of water. And taking that into consideration, we still have it that the products that are formed when water undergo ionization include hydrogen ions and hydroxy ions. So pH and pOH. pH and pOH. The production of this hydrogen ion and hydroxy ions give rise to the concept of pH and pOH. pH standing for the power of hydrogen ion concentration, and pOH standing for the power of hydroxy ion concentration. These two concepts are very important in the sense that they have some physiological effects. There are physiological implications of having a solution that is more acidic, and as well as a solution that is more alkaline. When these solutions are ingested or when they come in contact with the body, they have a way of affecting the body negatively or positively. That is why we are talking about it. That is why it is important that this concept be looked into. And that is why it is important to determine the pH of a solution. So in terms of color changes, the red color is assigned for hydrogen ion concentration, and a blue color is assigned to hydroxy ion concentration. The reason is that when indicators are used to check or to determine whether a solution is acidic or alkaline, for a solution that is acidic, the indicator tends to change to red color. Then for a solution that is alkaline, the indicator changes to blue. Also, to further explain this concept of acid and base using indicators, there is a bar chart here that I'm looking at, and at the extreme left of the chart there is an increased hydrogen ions and a decreased hydroxy ion, which shows that the solution is acidic. Then at the extreme end there is an increased hydroxy ion and a decreased hydrogen ion, which shows that the solution is alkaline. Then midway, in the middle of the two charts, the concentration of hydrogen ions and the concentration of hydroxy ions are equal, giving a neutral solution. pH scale. The pH scale is a graduated scale ranging from 1 to 14 that explains the level of acidity or alkalinity of a solution. So this scale is divided into colors. So color 1 and 2, which are intensely pink, shows a solution that is strong, that is a strong acid. Then from colors 3, 4, 5 to 6 is an indication of a solution that is a weak acid. Then at color number 7 is an indication of a solution that is neutral. Then from colors 8, 9, 10, 11 and 12, it shows a solution that is weak alkali. Then 13 and 14 shows a solution that is a strong alkali. The quantity of hydrogen ions in solution can affect the color of certain dyes found in nature. These dyes can be used as indicators to test for acids and alkali. An indicator such as litmus, which is obtained from lichen, is red in acid. If base is slowly added, the litmus will turn blue when the acid has been neutralized. At about 6 to 7 on the pH scale, other indicators will change color at different pH. A combination of indicators is used to make a universal indicator. So what that means is that these colors tend to change as the dynamics of the solution moves from being an acid to being a base, or from being a base to being an acid. So as the dynamics of the solution moves, is changed, these colors also change along. So determination of pH using indicators. Indicators are dyes that are used to check whether a solution is acidic or alkaline, and the principle is based on the fact that the concentration of hydrogen ions and hydroxy ions tend to cause some natural dyes to change from one color to another. So these dyes are used to check whether a solution is alkaline or acidic. There are another way of checking whether a solution is alkaline or acidic is by using a pH meter. A pH meter is an instrument that is developed to contain electrodes. I hope you know what electrodes are. Electrodes are negative and positive terminals of an electrically sensitive instrument. So by virtue of the charges, positive and negative, when a solution that has been ionized bearing hydrogen, which are positively charged, and hydroxide, which are negatively charged, come in contact with the electrodes, you know the law of opposite charges attraction, it will take place. The positively charged hydrogen ions will tend to move to the negative electrode, and the negatively charged hydroxy ion will tend to move to the positive electrode, thereby enabling the instrument to calculate the amount of these ions and display. pH can be measured in several ways. Usually it is measured with a colored acid-base indicator or a pH meter that I just explained. Colored indicators are a crude measure of pH but are useful in certain applications. Crude in the sense that they have a lot of limitations in terms of specificity. So it's just a quality. It will only give you a qualitative result by your ability to identify colors, but they will not give you numerical figures, which is more accurate, and that is what the pH meter does. So the pH meters are more accurate, but they must be calibrated prior to use with a solution of known pH. Yes, calibration is a way of reprogramming the machine such that it does not give a biased result, so that it does not give a positive result or a negative result when the reverse is the case. Okay, for instance, a negative positive result occur when a solution is actually acidic, but using the pH meter you see a value that is of alkaline. So that's a positive, a negative positive result for the acid. Then for the base, when the solution in actual terms contain more or higher number of hydroxy ions, but the pH meter is giving you the result that portrays the solution to be an acid. Okay, so to avoid such things, the pH meter must be calibrated, must be reprogrammed, so that it gives the actual result, and that is what it means by calibration. So limitations of pH scale. The pH scale ranges from 0 to 14, like I stated earlier. Now, what are the limitations? Values outside this range are possible but do not tend to be accurate, because even strong acid and bases do not dissociate completely in highly concentrated solutions. So what that is telling you is that whereas the pH range, the pH scale gives a range of 0 to 14, it is still possible to have pH values outside this range. That is, it is possible to have pH values of less than 0, that is minus a particular number. And it is also possible to have a pH that is over 14, but because one is only restrained to this range by using the pH meter, any numbers outside this range cannot be captured by the pH meter. That is one limitation. And the second limitation is that pH is confined to dilute aqueous solution. What does that mean? What that means is that a solution that is not dilute and is not aqueous will be difficult to determine its pH. It will be difficult to determine the pH of such a solution. So for a solution's pH to be measured or to be measurable, it must be dilute and aqueous. So that's another limitation. Because we know that we have other solutions that are not dilute and are not aqueous, yet they are solutions, but in such circumstances the pH cannot be measured, so it's a limitation. The temperature affects pH. That is why you have different temperature ranges, and they are corresponding equilibrium constants of water. So at 0 degrees centigrade, the equilibrium constant of water is 0.114 times 10 raised to power minus 14 moles square per liter square. Then for temperature, at temperature of 10 degrees centigrade, you have 0.293 times 10 raised to power minus 14. At 20 degrees centigrade, it is 0.681 times 10 raised to power minus 14. At 25 degrees centigrade, it is 1.008 times 10 raised to power minus 14. At 30 degrees centigrade, it is 1.471 times 10 raised to power minus 14, and so on. So what that means is that at different temperatures, you have different equilibrium constants of water. So the Kw, which is the equilibrium constant of pure water, decreases as the temperature increases. So an increase in temperature decreases the Kw. So at 25 degrees centigrade, the Kw equals to 1 times 10 raised to power minus 14 moles square per liter square. That means the concentration of hydrogen ions multiplied by the concentration of hydroxy ions equals to 1 times 10 raised to power minus 14 moles square per liter square. This equilibrium constant is very important because it applies to all aqueous solutions, be it an acid, be it a base, be it a salt, or even non-electrolytes. It is not just applicable to pure water. So theoretically, we can calculate the dissociation equivalent of water as this. The hydroxy ion equals the hydrogen ion, and the constants for the hydrogen ions and hydroxy ion are both 1 times 10 raised to the power minus 7. So 1 times 10 raised to the power minus 7 for the hydrogen ion multiplied by 1 times 10 raised to the power of minus 7 of the hydroxy ion will give a total of 1 times 10 raised to the power minus 14. So hydrogen ion produced from water at 25 degrees centigrade is 1 times 10 to the power minus 7 mole per liter. So replacing hydrogen ion concentration with pH to indicate acidity of solutions, pH 7 replaces hydrogen ion concentration of 1 times 10 raised to the power minus 7 mole per liter, where pH equals to the negative logarithm to base 10 of hydrogen ion concentration. So pH describes both hydrogen ion and hydroxy ion. What that means is that when we say pH, we are not just referring to hydrogen ions, but it's a broad term that describes both hydrogen ion and hydroxy ions. So on a scale of 14 to 0 in descending order, at between 0 and 14, the pH, at between 0 and 7, the pH equals to 0. Then at neutral pH, which is 7, the hydrogen ion concentration is equal to 10 raised to the power minus 7. Then at basic pH, for a solution that is basic, the hydrogen ion concentration equals to 10 raised to the power minus 14, and the pH is 14. Then for such a solution, the pOH equals to 0. and the concentration of hydroxy ion equals to 10 raised to power 0. So in essence, an acidic solution has a pH equals to 0 and a pOH equals to 14. A neutral solution has a pH equals to 7 and a pOH equals to 7. Then a basic solution has a pH equals to 14 and a pOH equals to 0. pH of common substances. There are a lot of substances we come across in our daily lives, and these substances are significant in the sense that we tend to come in contact with them either by ingesting them or by making use of them, and in one way or the other they affect our physiological being. So it is important to know their pH, and that is why that has been done, so that we can have an idea of the kind of substances we are dealing with, whether they are acidic or basic. So on this scale, 1 molar HCl has a pH of 0. Gastric juice has a pH of 1.6. Lemon juice has a pH of 2.2. Vinegar has a pH of 2.8. Carbonated beverage has a pH of 3.0. Orange has a pH of 3.5. Apple juice has a pH of 3.8. Tomato has a pH of 4.2. Coffee has a pH of 5.0. Soy has a pH of 5.5. Bread has a pH of 5.5 too. Potato has a pH of 5.8. Urine has a pH of 6.0. Milk has a pH of 6.4. The implication is that these substances are all acidic. Then water, of course pure water, has a pH of 7.0. Then drinking water has a pH of 7.2. Blood has a pH of 7.4. The implication is that these substances are neutral in pH. That is, the concentration of hydrogen ion equals the concentration of hydroxy ions. Then we have other category of substances that are basic, and they include detergents, bile, seawater, milk of magnesia, ammonia, bleach, and sodium hydroxide. These category of substances are basic in nature because their pH ranges from 8 to 14. Again, we have a chart of different substances with their pH for us to see. Then in terms of color change, when the color change increase up to blue, the pH is said to be alkaline. Then when it increase in the intensity to pink, the pH is said to be acidic. So calculation and practice for pH, pH has to do with numbers and figures, and it is often necessary to calculate the values of pH. So for us to be able to calculate the values of pH very effectively, there are fundamental terms we need to be familiar with. One, that the hydrogen ion concentration equals to 10 raised to the power of minus pH. Then hydroxy ion concentration equals to 10 raised to power minus pOH. Then again, pH equals to the negative logarithm to base 10 of hydrogen ion concentration. Then pOH equals the negative logarithm to base 10 of hydroxy ion concentration. So in all, when we add the values of pH plus pOH, that will give us 14. Again, there's a chart here that needs memorization. And what is that chart? That pH is equivalent to hydrogen ion concentration at the top. Then pOH is equivalent to hydroxy ion concentration. Again, that pH equals to the negative logarithm to base 10 of hydrogen ion concentration, where the hydrogen ion concentration equals to 10 raised to the power of negative pH. Then the concentration of hydroxy ion equals to 10 raised to the power of negative pOH. Why pOH itself equals to the negative logarithm to base 10 of the hydroxy ion concentration. So mathematically, pH plus pOH equals to 14. Again, hydrogen ion concentration multiplied by hydroxy ion concentration is equal to 1 times 10 raised to the power of minus 14. So these fundamental expressions are key for us to memorize, for you to memorize. So strong acids and strong bases. What makes an acid a strong acid? So an acid is said to be strong when it dissociates completely in solution. Then strong alkalis or bases also dissociate completely in solution. So any acid that does not dissociate or ionize completely in solution is not a strong acid. Likewise, any alkali that does not dissociate completely in solution. So it is easy to calculate the pH of strong acids and strong bases. All you need to know is the concentration of the acid or the base. So that takes us to some simple mathematical problems involving pH. And number one is that what is the pH of a solution with the concentration of 0.02 molar? Again, remember we were told that all we need is to know the concentration. And when we know the concentration, all we need to do is to replace hydrogen ion concentration with that concentration value that is provided. The same thing in number 2, where we are asked to calculate the pH of a solution of sodium hydroxide having a concentration of 0.0050 molar. All you still need to do is to replace this number 0.0050 molar with, all you need to do is to replace the hydroxy ion with this number. So in the case of number 1, when 0.02 replaces hydroxy ion, all you need to do is to take the negative logarithm to base 10 of this number, which is 0.02, and that gives 1.6989. Expressing it in 2 decimal places gives 1.70. Then in the second instance, replace hydroxy ion concentration with 0.005 molar. That gives 2.3. But remember that in this case, what you have calculated, this 2.3, is the pOH. Okay, is the pOH. So how do you get the pH? from the pOH is by subtracting the value of the pOH from the total value of pH on the scale, which is 14. So in this case, it's going to be 14 minus 2.3. That will give 11.7. Then number 3, you are to determine the pH of a solution where the hydrogen ion concentration is 7.2 times 10 raised to the power minus 8. Again, pH equals the negative logarithm to base 10 of hydrogen ion concentration. So replace hydrogen ion concentration with 7.2 times 10 raised to the power minus 10. That is going to give you 7.4. And 7.4 is away from the neutral pH of 7, on the right hand side. So that makes the solution to be slightly alkaline or slightly basic. So if you are given a problem, a follow-up question may come for you to indicate whether the solution is acidic or alkaline. All you need to do is to look at the figure in your calculation. If it is less than 7, it means it's alkaline. If it is if it is less than 7, it means it's acidic. If it is above 7, it means it's alkaline. If it is exactly 7, it means it's a neutral solution. So pH of dilute aqueous solution of strong acids. So we have already stated that strong acid dissociates completely in solution. So we have monoprotic. Monoprotic means 1 proton. Diprotic means 2 protons. And these protons here refers to the number of moles. So in an example where you have HA, an unknown solution, HA aqueous, dissociates to give you H and H plus 1 and A minus 1 or 1 minus, and the molar concentration of HA is 0.3. It means that the molar concentration of H1 plus will also be 0.3, and the molar concentration of H1 minus will also be 0.3. Why is it 0.3, 0.3, 0.3? Because in balancing the equation, the number of moles is 1. So the same concentration you have for the parent substance that is undergoing the dissociation or ionization will cut across, the same concentration will cut across the new products that are formed, which are the ionized forms. So for a diprotic solution such as H2SO4, the tetroxylcyclic acid, indicated as H2A, dissociating to give you 2H1 plus, then plus A2 minus. If the molar concentration in the parent substance is 0.3, then the molar concentration for the H raised to the power 1 plus will be 0.6, because there is a 2 in front there. There is a 2 in front of the hydrogen, which means that 1 mole of the parent molecule produce 2 moles of the acid and 1 mole of the base. So you are going to multiply the concentration of the acid by 2. So in this case, 0.3 times 2 will be 0.6. So again, in trying to revise, pH equals to negative logarithm to base negative logarithm to base 10 of hydrogen ion concentration. Given that the pH of a substance is 4.6, determine the hydrogen ion concentration. The first thing to do is you memorize the equation. You choose a proper equation, which is pH equals to the negative log raised to base 10 of hydrogen ion concentration. Then the next thing to do is to substitute pH value in the equation. What are you substituting pH value with? With the 4.6, because you have been provided that the pH value is 4.6. So it's going to be 4.6 equals to negative log raised to base 10 of hydrogen ion concentration. So the next thing is to multiply both sides by -1. So if you multiply 4.6 by -1, it's going to be minus 4.6. That will be equal to negative log 10 to base 10 of hydrogen ion concentration. So the next thing is to take the antilog of both sides. So for you to take antilog using your calculator, you press second function, then you press log. So the antilog of 4.6 is going to give you 2.51 times 10 raised to the power of -5 molar. So you can verify this number, you can check this answer by working backwards. So pH, working backward now, pH equals to negative log raised to base 10 of hydrogen ion concentration. So taking it backward, you replace hydrogen ion concentration with 2.51 times 10 to the power of -5. So that's going to give you the same value that was given initially, 4.6. So going further, we are going to be looking at the pH calculations for weak acids and weak bases. Remember, the one we just finished looking at is the pH calculation. Was the pH calculation for a strong acid and base. This time around is that of a weak acid and base. So for weak acid and base, pH equals to the negative log raised to base 10 of the square root of Ka times concentration of acid. Ka stands for the equilibrium constant of the acid times the concentration of the acid. Then for weak bases, POH equals to log raised to base 10 of Kb times concentration of the base. Again, Kb is the equilibrium constant of the base. So pH is going to be equal to 4 minus POH. Again, in calculating the pH of weak acids, first of all, a weak acid is one which only partially dissociates in aqueous solution. A weak acid indicated by Ha will dissociate as follows. Ha in a forward and backwards reaction will give you hydrogen ions and A minus and A minus, but these are sparingly soluble. They are not completely soluble in solution. So Ha in a forward and backward reaction will give you hydrogen ions and hydroxy ions indicated by A minus. So applying the equilibrium law, that will give us an equilibrium constant of the acid, that is Ka. Ka stands for equilibrium constant of the acid, equals to the hydrogen ion concentration in aqueous form multiplied by the hydroxy ion concentration indicated by A minus divided by HA, and the unit is moles per dm cube. The ions are formed in equal amounts. What does that mean? That means that the hydrogen ion concentration equals to the hydroxy ion concentration. Remember, A minus stands for hydroxy ion concentration. Therefore, the equilibrium constant of the acid will be equal to the hydrogen ion concentration square divided by the HA. HA stands for the acid, that the acid before dissociation. This HA stands for the acid before dissociation. This is after dissociation. This is before dissociation. So we are dividing it by the acid before dissociation. So in rearranging this, it will give hydrogen ion concentration square equals to the acid multiplied by the equilibrium constant of the acid. Therefore, hydrogen ion concentration equals to the square root of the acid multiplied by the equilibrium constant of the acid. So for pH of solutions of weak concentrations, weak acid, pH of a 1 molar solution of ethanoic acid with an equilibrium constant value of 1.8 times 10 to the minus 5. So this is an example of the previous explanation. So ethanoic acid is an example of a weak acid. So pH equals to the negative logarithm to base 10, the square root of the equilibrium constant of the acid, that is the ethanoic acid, multiplied by the concentration of the acid, and all of these are given in the question. So pH equals to negative log to base 10 of 1.8. Remember, 1.8 times 10 to the 5 is given here, multiplied by 1. 1 is the concentration, 1 molar concentration of ethanoic acid. So the pH will be 2.3723. So again, pH of solution of weak concentrations. This time around we are considering a weak base. Initially it was a weak acid. So it's the same formula. The only difference is that this time around we are dealing with Kb, which means the equilibrium constant of the base, and of course the concentration. So POH, substituting all this into the equation, you have POH equals to negative logarithm to base 10, the square root of 1.8 times 10 to the minus 5 times 0.2. 0.2 is the molar concentration of the base as given in the question. So that will give, taking the square root of this, it will give 2.7319. Now remember that this 2.7319 is the POH, because what you just calculated here is the concentration of hydroxy ions, but in the question it is the pH. So to get the pH, you simply subtract this number from 14. That will give 11.2681. And again, remember that pH has no unit. So moving on, we are going to be looking at the shapes of titration curves. I want to believe you know what titration is. Titration, in simple terms, refers to a reaction, an experiment that involves the reaction between an acid and a base. So because we have already looked at the different types of acid and base, strong acid and strong base, we're also going to be looking at their titration curve. Titration curves, or a titration curve, is simply a graphical illustration of the reaction between the acid and the base. So because they display different patterns, it is important for us to look at those patterns. So these patterns are as shown in the graphs here. So when a strong acid reacts with a strong base, this is the pattern. This is the pattern. You have on the y-axis the scale of 0 to 14, which is the pH range. Then on the x-axis is the volume of the alkali that was added. Remember that in the reaction of an acid, in the titration of an acid against a base, the acid is run from a burette while the base is in a beaker through which the acid runs. And remember that in the beaker, what you have is a pipetted or a pipetted, as you may wish to call it, volume of the base. So it's not arbitrary. And remember that the volume of the pipette is usually 25, or although there are pipettes that are more or less, but let's consider a pipette that is that can carry 25 cm3. So assuming you pipetted 25 cm3 of the base into a beaker, and you are running the acid through it, remember a time will come when the color will change. You know, there will be a color change, and that point, immediately the color changes and you confirm that the color has changed, that point is referred to as the end point or the equivalent point. So in trying to know the pattern or the curve, at that point you are expected to stop and trace the mark where it stops. And once that is done, you will have a pattern that is in S shape. That is for a strong acid against a strong base. Then another one is when you are titrating a strong acid against a weak base using the same titration methods. The acid in the burette, the base in the beaker. You will discover that the pH, this is the pH range. The pH range for a strong acid against a weak base is not the same as the pH range of a strong acid against a strong base. You can see that the pattern of a strong acid against a strong base gives an equivalent point where the pH is almost 7. So I can call this 6.9999. But when it is a strong acid against a weak base, the pH is far less than 7. Looking at it, even though the shape is also an S shape, but the pH values are not the same. That of a strong acid against a weak base vary. So what is the interpretation? What is the implication? The implication here is that you have added more acid than base. The volume of acid that brings these two to a neutral point or to an equivalent point or to an end point is more than the number of, the volume of the base. But in the case of a strong acid against a strong base, the volume are almost the same. That is why you have a pH almost 7. Remember we said earlier that at pH 7 the number of hydrogen ions and the number of hydroxy ions are the same. So looking at these patterns, you will understand that the difference is in the amount of hydrogen ions you are introducing into the solution. So now let's consider a weak acid against a strong base. You can see that the pH has gone way above 7. What is the implication? The implication is that a higher amount of the base is required. So if you are to run this acid through a burette, we discover that the volume of the acid that has that gives you a color change is quite small compared to the 25 for the base. Then a weak acid against a weak base, it is an entirely a different pattern here, where you have the equivalent point at a pH that is almost 7. So the implication here is that more of the acid and more of the base are required to bring the reaction to the end point. So choice of indicator in for titration. Indicator must have a complete color change in the vertical part of the pH titration curve. Indicator must have a distinct color change. Indicator must have a sharp color change. Then indicators for strong acids, strong base titration. So just as I explained earlier, you see the pattern. And for a strong acid against a strong base, the preferred indicators are phenolphthalein and methyl orange. Then both phenolphthalein and methyl orange have a complete color change in the vertical section of pH titration curve. That's why they are suitable indicators. Then indicators for strong acids, weak base titration. Methyl orange is used as indicator for this titration. Only methyl orange has a complete color change in the vertical section of the pH titration curve. Phenolphthalein has no complete color change in the vertical section. So here methyl orange is a better indicator, would be a better indicator for the reasons stated above. Then indicator for weak acids against strong base titration. Phenolphthalein is used as indicator for this titration. Only phenolphthalein has a complete color change in the vertical section of the pH titration curve. Methyl orange has no complete color change in the vertical section. So phenolphthalein makes a better or the best indicator in this type of titration. The indicator for weak acid against a weak base. Here, no indicator is suitable for this titration because there is no vertical section. So neither phenolphthalein nor methyl orange have completely changed of color in the vertical section of the pH titration. So color changes and pH ranges. So using litmus paper, from pH above 7 up to 14 there is a deep blue coloration. Then pH of less than 7 down to 0 there is a sharp pink or red coloration. Then when methyl orange is used, there's a sharp yellow coloration or color change for the alkaline, and then a sharp red or pink coloration for the acidic solutions. Then for phenolphthalein, there is a sharp pink coloration for the alkaline solution, while there is no color change for the phenolphthalein for the acidic solution. Then of course these are the colors as you can see in the glasses in the conical flask. Methyl orange, pH equals to 2. At pH equals to 2 it gives a pink color. At pH of 7 it gives a yellow color. Then phenolphthalein at pH 7 there is no color. At pH 10 gives pink. Then there is also a color chart here for you to see. Thymo blue and methyl orange give red colors at low pH. Then bromo, thymo blue and thymo blue in second transition give yellow, but phenolphthalein gives a colorless solution. Then in transition pH range, you have orange and yellow for thymo and methyl orange respectively. Then you have blue for bromo, thymo and thymo. Then you have purple for phenolphthalein. So with that, I would like us to end the class for this session. If there is any question, you can send them across. So in addition to that, you have an assignment, and the assignment is that what is the pH of a solution containing 0.009 molar H2SO4, that's a tetraoxide acid, and 0.05 molar sodium hydroxide. Second question is calculate the hydrogen ion concentration of a solution of pH 2.5 times 10 raised to power minus 6 molar, and state whether the solution is an acidic or an alkaline solution. Thank you for listening. We'll meet again in the next class.